Hello, and welcome to another lovely session of Civil Engineering with Tanya J. Laird. I am the aforementioned Tanya J. Laird. This video is the 15th in our wood design series. In this video, we will be learning about the effects of time on the strength of wood and lumber. We will be doing a deep dive into the ASD load duration factor and the LRFD time effect factor. Today's lovely music comes fittingly from the artist Unheard Music Concepts from the album The Lasso of Time. A link is included in the video description. As we have discussed at length in this series, wood is a composite material with quite complex behavior. We've seen that it's orthotropic and has different strengths depending on which direction it is loaded. We've seen that changes in moisture content affect its dimensions. We've seen that numerous local and global defects result in different grades having different allowable strengths, even for wood of the same species. Today, I wish to talk about another of wood's unique behaviors, and that is the relationship between load effects and time. To illustrate this property, let's first imagine a steel beam with a load across it. The instant the load is applied, the beam is going to deflect a certain amount. Obviously, the drawing shown here is exaggerated, but a steel beam will deflect under load. But what if I leave that load there for an hour, for a day, or for a year? Does the beam sag still further? With a material like steel, the answer is no. There is no long-term, time-dependent behavior of steel elements under normal conditions. Now, if the beam is loaded past the yield strength, then such behavior can be observed. Or if the temperature of the beam is highly elevated, this kind of time-dependent observation can occur. And by elevated, think the building is on fire, not the air conditioner is broken today. Under normal conditions, a steel beam will have a single deflection value regardless of the load duration. That load could sit there for a millennium. As long as the beam didn't degrade or deteriorate, it would exhibit the same deflection 1,000 years from now as it does the instant that I apply the load today. But not all materials are like this. Concrete, for instance, exhibits long-term increased deflection, and so does wood. Consider this graph by Gerards. In this study, 2x4s were loaded in bending, and the total load was allowed to persist unchanged for up to 12 years. This measures what is referred to as creep deflection. In other words, deflection beyond the initial deflection. All of the deflection shown here is additional deflection produced by a constant load over time. This specimen initially deflected 0.344 inches, but over the next 12 years, its total deflection nearly tripled. Again, this is with the same exact loading consistently applied to the specimen. Wood, like concrete, exhibits time-dependent response to loads. Now, why does this happen? Well, researchers have found that there are several mechanisms at play, and I'll just highlight one of them here. Remember back to our analogy of wood as a series of straws bound together. Well, how are those straws actually bound? One of the mechanisms is through hydrogen bonds between adjacent cellulose chains. When lumber is loaded, adjacent cellulose chains will want to slide past one another. This is prevented by the hydrogen bond, indicated by the small black circles here. However, under prolonged loading, the chains can slip, break, or deform. Over time, this can result in the chains slowly moving past one another. This process relies on statistical chances and random molecular movement, so it's a very gradual process. But over time, the deflection will magnify. Over time, this deflection can even become permanent. This kind of behavior occurs in many types of loading in wood. While this can be seen as a deflection magnification, it also affects stress. Shown here, consider a tension member. When under tension, the amount of material in an object doesn't magically change. In fact, its total volume is largely unchanged. Under tension, an element elongates. In turn, its cross-sectional area has to slightly decrease. However, the force it carries remains constant. If the force remains constant while the area decreases, then the stress inside it at any section that decreases in cross-sectional area must increase. Thus, elongation of a member slightly increases the stress inside a member. This is why this kind of long-term creep also affects not just deflection, but stress. These time-dependent deformations will tend to amplify stresses inside wood members, and thus this is a concern not just for serviceability, but to safety. So, the NDS specification has two methods of dealing with the time-dependent effects of load, depending on whether the design is being conducted as ASD or LRFD. First, let's consider ASD. The reference design strengths provided in the NDS supplement are calibrated for what are considered normal duration loads. These loads have a 10-year duration, or more precisely, they are anticipated to occur at their maximum value for a total of 10 years over the life of a structure. While live loads such as furniture will nearly always be present in a building, the maximum live loads will only occur occasionally. In other words, a maximum live load would mean all furniture, all, if it's an office, it would mean like all furniture, all paperwork, all, any filing cabinets are full, the maximum number of people are in the office, that sort of thing. So so a normal duration load is one that has its maximum value expected to occur over a period of a total of 10 years over the structure's design length. So thus the 10-year assumption is valid for live load. This 10-year period is defined as the baseline normal duration load. Loads that occur over periods longer than this are more severe than the strengths assumed in the reference design strengths in the NDS supplement. Loads that occur on shorter intervals are less severe. So consider Table 2.3.2. Table 2.3.2 here illustrates how the load duration factor CD is obtained. CD is one of the adjustment factors that the reference allowable stress is multiplied by. Thus, a factor greater than 1 will increase your allowable stress, while a factor less than 1 will decrease your allowable stress. Consider impact load, which is near instantaneous. Here, the CD factor has a value of 2. In other words, the allowable stress of the member is doubled. Now, as always with the NDS and any other specification, pay special attention to the caveats, footnotes, and asterisks. Consider footnote 1. This states that the CD factor is not to be applied to elastic modulus values or to compressive strength perpendicular to grain. This is because those load duration factors are calculated for load, not displacement. The elastic moduli are related to stiffness and deformation, not allowable stress. The compressive stress perpendicular to grain is an interesting one. You are not allowed to use the CD factor in that case because these stress values are actually based on a deformation limit. Stresses perpendicular to grain cause crushing of the wood fibers, and the code defines the stress value, or the allowable stress value, based on an acceptable upper limit on the amount of crushing that's allowed. The second note prohibits a value greater than 1.6 to be used for any connections, wood structural panels, or for pressure-treated lumber. The pressure-treated lumber or the fire-retardant treated lumber relates just to the how the potential for these chemicals to perhaps decrease some of the bond strength between the wood fibers, and the limiting it to 1.6 on the connections and the wood structural panels is just a little bit about being a little extra conservative on the connections, and also has to do with how loads transfer through a structure. And so these are just additional safety considerations that have come out of various research efforts. Now, there is one other very important note when using these numbers. Usually we're dealing with members with more than one load applied at once. For example, let's say a beam has both dead and live load applied to it. Dead load has a load duration factor of 0.9, while live load has a load duration factor of 1.0. So, which do you use? you're going to multiply, remember, you're going to multiply the reference design strength by this factor, so you can only use one of them. Now, it would certainly be more conservative to multiply by the smaller value, thus decreasing the allowable stress. However, as shown here, section 2.3.2.2 states that we use the CD value for the shortest duration load present. Thus, if you have both dead load and live load on a beam, you use a CD of 1.0. While this may seem under-conservative, the key to realize is that all of the loads are going to be compared against this value. Live load won't be present with a permanent duration, and it's the total load that contributes to the long-term duration effects. Thus, the NDS instructs that you use the greatest CD value applicable to any of the loads present in the critical load combination of your analysis. Next, let us consider NDS table N.3.3. This describes the time effect factor. This serves the same purpose as the previously discussed load duration factor, except this is applicable to LRFD rather than ASD methods. Different lambda values are applied depending on which load combination is used. Again, this value is going to be multiplied by the design strength, so a lower number will decrease the calculated capacity of a member. Also, there is a comparable caveat here. As provided in Note 1, a factor greater than 1.0 shouldn't be used for a connection design or for a pressure-treated or for a piece of pressure-treated lumber. And these numbers are different than those in the previous load duration factor table, simply because they are statistically calibrated for the load and resistance factors found in LRFD design than the values used in allowable stress design. Alright, and I think that will do it for today. This video is just a short introduction to the effects of time and load duration on the strength of lumber. We discussed why the strength of wood is affected by the duration of loading and how the NDS takes this into account for both ASD and LRFD methods. If you have any questions, please leave them in the comments below. If you found this video useful, please like, comment, and subscribe to make the YouTube robots happy. If you want to help make content like this possible, see the link to our Patreon page in the video description. Regardless, we'll be back soon with another video in this series. I look forward to seeing you all then, and as always, thank you.